Right. Okay, before the start, let me just a few news. The second homework is the deadline has passed yesterday. I hope that all of you remembered about it. The deadline for the third homework is in 2 weeks, right? Yeah. So you can see the homework assignment on the web page. So we continue today with the applications of generalized coloring numbers. And something that I was that we were looking at the end of the last lecture was these notions of domination and independence in graph. So let me just recall that a set D is a distance R dominating set in a graph G. Yes, if, let me write it concisely, if I take all the vertices of my dominating set, and for each of them I take the ball of radius R in the graph G, let me write it like this, in the graph G I take a ball of radius R, so the distance R neighborhood of the vertex, this consists of all the vertices at distance at most R from U. Then this is the whole graph, the whole vertex. Yes, so every vertex is at distance at most R from one guy from the dominating set, right? So this was the domination number. And second thing is the independence number, namely I is a distance R independent set in G if the vertices of I are pairwise at distance more than R. Yeah? So distance 1 dominating set is the classic dominating set, distance 1 independent set is the classic independent set. Yes? So now we had this observation that actually I is a distance 2R independent set if and only if the balls of radius R around the vertices of I are disjoint. Right, so to see it on the picture, I've got my graph. I have my vertices of my distance 2R independent set, and the fact that they are pairwise at difference 2R is the same as saying that if I draw a ball of radius R around each of them, then these balls should be disjoint, right? Good. So this gives me the standard corollary that that if I look at the domination number as distance R, so the smallest size of a distance R dominating set in my graph, yes, then this needs to be at least the independence number for distance 2R. Yes? Because if I have an distance 2R independent set like that, in order to dominate those centers of those balls, the vertices of my independent set, I need to pick at least one vertex to the dominating set from each ball. Because one vertex can dominate only one guy from this distance 2R independent set. Yes? So this gives me this inequality, and we have seen during the tutorials that the gap between this and this can be arbitrarily large. In the following sense, this, even for R equal to 1, independence number 2 can be equal to 1, while the domination number can be unbounded. Yes, there was an example during the tutorials. But the goal of this lecture, of the first part of this lecture, is to prove that actually in classes of sparse graphs, there is a linear relation between these two. Yes? So more precisely, we'll prove the following theorem. that let's C be a class of bounded expansion R is fixed, then for every G, for every graph from my class, I've got the following relation. If I take the domination number R, yes, then of course this is at least independent at distance to R. This is just this inequality. And this is upper bounded by the independence number even at this, okay, let's write it, at this, even at distance to R plus 1, yes, multiplied by the following constant, the weak coloring number, 2R plus 1 of the class square. Yes? Even, maybe I will not even write here the class, but of this individual graph. Yes? So note now that independence 2R plus 1, independence number at distance 2R plus 1, this is upper bounded by just the independence number at distance 2R, because it is easier to find a distance 2R independent set than a distance 2R plus 1. Yeah, so this is only, can be only larger than this. Yeah, and here I've got this. This number. Yeah, so actually in this statement, I did not even need this to specify this class, because, well, this is an inequality that just involves one graph. But observe that if C is a class of bounded expansion, these numbers will be always bounded by a universal constant, right? So the idea of this theorem is that on class of bounded expansion, there is a linear gap between the domination number for distance R and the independence number for distance 2R, right? Good, so this is the theorem that is stated here combinatorially, but what we will actually prove, so moreover, there is a polynomial time algorithm that given G from my class, oh, maybe just given G, and a vertex ordering with, let's say, VUCOL, let's call it sigma, at distance to R plus 1 bounded by some constant C, computes two things. First of all, it will compute D. This will be a distance R dominating set. And second, I, this will be a distance 2R plus 1 independent set. Yes? Such that the size of D is upper bounded by C squared times the size of I. Yes, so why this statement implies this statement? Yes? If my algorithm outputs something, then these two things exist, right? There is a distance R dominating set and a distance to R plus 1 independent set that satisfies this inequality. So in particular, on this side, this is larger or equal than the domination number R for the graph, yeah? Because this is a distance R dominating set, so it is larger or equal than the smallest possible size of a distance R dominating set. Yes? On the other hand, here, this is smaller or equal than this C squared, yes, times the independence number for distance 2R. Yes? Because this is some distance 2R, 2R plus 1. Because this is some distance 2R plus 1 independent set in my graph, yes? So, in particular, it is smaller or equal than the maximum possible size. Yes? So we get this inequality, Yes, and in order to get this bound, it suffices to take this sigma to be an ordering with the optimum weak coloring number. Yes? So then this implies this inequality by taking sigma with optimum vocal at distance to r+1. Good. So we are going to give this algorithm. Yeah? But before giving this algorithm, actually let me state the corollary of this in more algorithmic terms. Namely, I want to say that let C be a class of bounded expansion and R be fixed. Then I claim then distance R dominating set problem. So this is a computational problem. You are given a graph and you would like to output as good, as small dominating set in this graph, distance R dominating set as possible. Yeah, so this is an optimization problem, minimization problem. Then this problem has a constant factor approximation on C. Yes, which means that when the input graphs are restricted to graphs from C, then then there is an algorithm that always produces a dominating set whose size is at most some constant times the optimum. Yes? And dually, also the distance R independent set problem also has a constant factor approximation on this class, which means that there is an algorithm that again produces a distance R independent set whose size is at most at least the optimum over some constant. Yes? Because this is a maximization problem, this is minimization problem. Yeah? So how to prove it? Meaning the proof is just essentially symbol pushing here, apart from one fact that if I'm given a graph G, yes, from my class in polynomial time, we can compute some ordering sigma with the weak coloring number for distance R of this ordering bounded by some constant C depending only on the class and the radius R we are interested. Yeah? So this can be done, for instance, by computing admissibility and then using the bounds on the weak coloring number based on admissibility. Admissibility we did not show how to compute exactly, but we have given a factor R approximation, and R is considered here a constant. We can also use the fraternal augmentations that we discussed during the tutorials last time. So we have given plenty of ways of computing, given a graph from a class of bounded expansion, and ordering with bounded weak coloring number. Yes? So if I'm given this, then run the algorithm, run this algorithm, yes, and this gives me D and I, and now observe that the size of I, well, this is upper bounded by, as we said, c squared times the size of I, yes, which on the other hand is bounded by c squared times the independence number for 2r plus 1, right? Which, again, independence number for 2r, even. And this, by the inequality that we had here, is upper bounded by c squared times the domination number for distance r for g, right? So this shows us that the size of the output dominating set is at most c squared times the optimum one. Yeah, so this is a constant factor approximation what we output. And for I, the same. Yeah, you just give the same reasoning, and you obtain that this is again a c square factor approximation of the optimum distance, actual distance to r plus 1, both distance to r plus 1 and distance to r. Yeah, so I wrote here r, but I should run this algorithm for actually something like r half. Yes? So by this argument, I have this 2r plus 1. Maybe I can write it down. Yeah, the size of I is at least the size of d over c squared. Yes, which is at least the domination number r of g over c squared. Yes, which is at least the independence number for 2r. Yes, of g over c squared. Yes. Which on the other hand is at least the independence number for distance to r plus 1 of g over c squared. Yes? So this inequality means that this I, which is distance to r plus 1 independent, is both a constant factor approximation for distance to r independent sets and for distance to r plus 1 independent sets. Yes? So we take both this even number and this odd number at the same time. Yes? So we can cover all integers like that. Good. So this is the corollary of this stated in algorithmic terms, and we are now ready to prove this theorem. So let me arrange it. So recall that the input is my graph, and the ordering sigma, and I have the assumption that the weak coloring number 2r plus 1 of this ordering sigma is bounded by some constant c. So the algorithm will work as follows. It will be greedy. Yes, and then we will argue that this greedy actually gives you a good approximation guarantee. So we will maintain three sets. The first set will be D. So this is at the end of the algorithm, this will be a distance R dominating set. Yes? There will be another set A. I will call it a pre-distance to R plus 1 independent set. In the following sense that we will try to make it in the distance to r plus 1 independent set. It will not be a distance to r plus 1 independent set at the end of the algorithm, but then we will find a large enough distance to r plus 1 independent set within A. So A is a mean to construct a large distance to r plus 1 independent set. Yes? And finally, there is a set R for the rest. These are yet undominated vertices. So the algorithm starts by setting D to be the empty set, A to be the empty set. So far we did not put anything into the dominating set nor into the independent sets. And the rest, the vertices undominated by the, not dominated by D, this will be the whole graph. So more formally, we will maintain the invariant that R are precisely vertices not distance R dominated by D. Yeah? Good. So now, how the algorithm works. Actually, I will write a pseudocode here. Yeah? It will be really easy, and this is why I can actually write a pseudocode. So while there is still a vertex that is not dominated, yes, so there is something to dominate, let me take the vertex that is smallest, undominated vertex that is smallest in my ordering sigma. So I look at R, yes, these are vertices that are not yet dominated. I take the smallest one that is not yet dominated in the ordering sigma. Yes? So what I do, I add it to A. Yes? Maybe I'll write it like that. Add U to A. And I add to D the following set, all the vertices that are weakly 2R plus 1 reachable from U. Yeah? So to see it on the picture, maybe here are vertices of R that are not yet dominated. I'm taking the smallest guy, this is vertex U. I'm adding it to A, and I'm taking its whole weak reachability set for distance to R plus 1, and I'm adding it to D. Yes? So all these vertices now get into the dominating set. Yeah, this is a super greedy move. There can be a lot of them, but their number is bounded by some huge constant. Yes? Okay, and then I update R, so remove from R all vertices distance R dominated by this W reach that we added. Yeah? And this is the whole algorithm. Yeah? Well, that's the whole algorithm. I did not tell you how we actually define I, the independent set. I will prove it, meaning this will turn, meaning this we will see at the end of the proof of the correctness, actually, of the approximation ratio. Okay, so is the algorithm clear? There is one technical implementation detail that I did not speak about here, namely how, given a vertex U, you compute which vertices are weakly reachable from it. Yes? But this is pretty easy. If I want to, from a vertex U, check whether a vertex V before it is weakly reachable, yes, then what I do in the graph, I just remove temporarily from the graph all the vertices before V, yes, and I just run a BFS to see what's the distance. Yes? So that's, and then I just check every vertex V to see whether it's weakly reachable from U. This is maybe suboptimal, you can probably do it in linear time, but we are just aiming at a polynomial time now, so we don't care. Yes? Good. So this is our greedy algorithm. So now let's see some properties of the set A and the set D that we produce at the end. So first of all, and this should be sort of clear from our invariant and from when this loop stops is that at the end, of course, D is a distance R dominating set. Right? Because we had the invariant that rest are precisely the vertices not dominated, and we stop when nobody else is not dominated. Yeah? Okay, second thing that we have is that actually the size of D is bounded by C times the size of A. Yeah? Because every time we were adding one vertex to A, we added at most C vertices to D. Yes? So the ratio between the size of D and the size of A is always bounded by C. Yeah? So it suffices now to show that A contains a distance 2R plus 1 independent set call it I of size at least the size of A over C. Yes? That maybe this A itself is not yet a distance to R plus 1 independent, but still we can find in it a large distance to R plus 1 independence. Yeah? Because if we have this, then what we see that the size of D is upper bound by the C times the number of A, which is upper bound by C squared times the number of size of I. Right? Yes? And this will be the dominating set and the independent set that we will output at the end. Yeah? So now it suffices to prove this claim. Yeah? Good. I will actually prove a stronger claim as follows. So suppose that I've got my vertex A from A, let's say. So for every vertex A from A, there are at most let's say C minus 1 vertices B from A such that the distance between A and B is at most 2R plus 1, and this B is before in sigma than A. So let's look at the picture. I claim that if this is sigma, and here I've got some vertex A belonging to A, and I think how many vertices to the left of it from A can be reached by a short path, then this number is bounded. If I here have B's from A such that the distance between these two vertices is bounded by at most 2R plus 1, then the number of such different vertices is at most C minus 1. This is my claim. Yes? Okay, so now why claim 2 implies claim 1? Well, we can do like a greedy coloring. So let's take A and let's color it with C colors. Greedy. So that I'm coloring vertices of A from left to right, yes, in the ordering sigma. And every time I'm taking another guy A from A, I'm looking at all the vertices from A before, that were colored before, and are at distance at most 2R plus 1. And I'm giving him a different color than the colors of all of those. Yes? If I have C colors, then I am able to make such a coloring. Yes? And then within every color, every two vertices are at distance more than 2R plus 1. Yes? So let me take the largest color, then the largest color has has size at least A over C. Yes? So to write it down, greedily color A with C colors so that every color is a distance to R plus 1 independent set, and we just put I to be the largest color. Yeah, and of course this is algorithmic. Yes? We can just run this greedy procedure coloring and take the largest color. Yeah, so this is how we will compute I. Good, so now we are left with proving claim 2. Yes. So the idea is as follows. Let me take this order. Let me take any A from A and consider any B from my set A that is before. Yeah, so B is smaller in the order than A. Yes? And also let me assume that the distance between A and B is small. Yes? So what we want to prove that the number of candidates for such B's is bounded. Yes? Is bounded by C minus 1. Yeah? So if this distance is small, this means that I can draw a path. Yeah? A short path. Maybe it goes like this. It can go below B, right? There is no reason why not. Yes? It's just distance in the graph. Yeah? So let then, that's the classic trick of all the arguments in with general coloring number. Let Z of B be the smallest vertex on this path P, let's call it. So here is the Z of B. Yeah? What do we know about the Z of B? Well, Z of B for sure belongs to the, well, then the prefix and the suffix of this path P witness that Z belongs to the weak reachability set for distance to R plus 1, both of A and of B. Right? Then I claim the following claim. So let's call this this prefix PA and this suffix PB. Yes? I claim that the length of PA is actually larger than R. Yes? That this path cannot be short. Yes? Why? Otherwise, what would happen? What did the algorithm do? The algorithm was adding consecutive vertices to A, yes, in order. Yes? Every time I was taking the smallest vertex into A from the undominated ones, so B was added to A before A. Yes? So when B was added to A, in particular I added Z of B to the dominating set. Yeah? Then z of b was added to my dominating set D. And when we were adding z of b to the dominating set D, yes, we removed from the remaining vertices to dominate, yes, all the vertices where distance r dominated from it. Yes? Then we removed the distance r neighborhood of z of b. Yes? But then if this path PA was of distance of length at most r, then when ZB was added to D, A would be excluded from R. Yes? So we could not take it in further iterations to A. Yeah? So then A would be removed. From R, and this is a contradiction because then it was added to A. Yeah? So we already know that the length of this PA is long, which in particular means that the remaining part of the path needs to be short. Yes? So the corollary of this claim is that the length of PB, yes, is always upper bounded by R. Yes? The length of the whole path is 2R plus 1, so if one part is larger than R, then the second is at most R. Yes? Good. Okay, now the next claim is that for different B, let's say B and B prime, looking like that, these vertices Z of B are different. So what I mean by this, if I have here my vertex A, and here I've got one vertex B and another vertex B satisfying those conditions, and I draw these paths for both of them, and I look at their ZBs, yes, Z of B prime and Z of B, then they need to be different. Yes? And the argument is again the same. Yes? So here I've got my suffix PB, and here I've got my suffix PB prime. Yes? So suppose that they actually are the same for the sake of contradiction. Yes? So the situation looks like more or less like this. Yes, there is one common ZB equal to ZB prime. Yes?
Actually, this PB prime is PA, isn't it? P prime on the picture. I mean,
oh, sorry, yes, of course. This is PB prime. Thank you. Yeah. So this suffix is PB prime. This suffix is PB. Yes? So from my first claim, I know that the length of PB of the suffix to this PB from this ZB is at most R, and the length of PB prime is also at most R. Let's suppose without a contradiction that the situation is like on the picture, that B prime is smaller in sigma than D. Yes? So what happened in my algorithm? When B prime was added to A, we added to D everybody that was weakly reachable from it, even at distance 2R plus 1. So in particular, we added this guy. Yes? But then B was excluded from R. Yes? Because it got dominated. Distance R dominated. So when B prime was added to A, Z of B which is the same as z of b prime, was added to D, and B was removed from R. And this is again a contradiction. Yes? So this is the proof of this claim, and from this claim we can actually finish the whole thing, right? Because if for different B and B prime I've got different ZBs, yes, then I see that the number of different possible ZBs, Z of B's, is at most, well, C minus 1. Yeah? Because each of them is weakly to R plus 1 reachable from A. Yes? And the weak reachability sets are bounded by C, and ZB is of course different than A, so I actually have C minus 1. Yeah? So we have at most C minus 1 possible Z of B's, and each of those Z of B's gives rise to at most one B that we take into account. Yes? So this concludes the proof. Yes, is the proof clear? It is quite a juggle with all those weak coloring numbers. This greedy procedure is quite natural at the benefit of hindsight in some sense. Meaning, once you look at it, yeah, it's natural to construct a greedy dominating set in this way. Yes, but you need to actually do some interesting analysis on these orders and to see why actually you are bounded. Yes, why the output is bounded. Good. So during the tutorials last time we have seen the approximation algorithm for the distance R dominating set. This was just this algorithm where everybody was just pointing at the smallest vertex in his weak reachability set. This gives you a constant factor approximation for the dominating set, but not for the independent set. Meaning that's the only way I know for approximating the independent set, the distance R independent sets at the same time as the domination number. Good. So this is the duality between the independent sets and dominating sets that I wanted to show during the first half of today's lecture. And now during the second half I want to give you another application of weak coloring numbers, one that I particularly like because it's very structural in a sense, you will see in a moment, namely that of neighborhood complexity. So what is this animal? Neighborhood. So I think it was tutorial number 2 when we were doing the following exercise. Namely, suppose you've got a graph G and you've got some subset of vertices A. And for a vertex U in my graph, the neighborhood in A is just, well, what the neighborhood in A should be. Yeah? So U is mapped to the closed neighborhood of U. So U together with all its neighbors, and I intersect it with A. So what are the neighbors of U in A? Yes? So now I can think of different vertices can have different neighborhoods. And of course, you can ask yourself how many different neighborhoods are realized in a graph. Yes? So if you look at all possible vertices of my graph and draw all possible neighborhoods, maybe some of them have the same neighborhood. Yes? So how many different neighborhoods are realized? Yes? So a priori in a general graph, well, every subset of A can be a neighborhood of some vertex outside of A, right? But you see that then there is a lot of connections between the remaining vertices and A. So the intuition is that maybe in a sparse graph, actually the number of different neighborhoods is smaller. Yeah? And this is what we proved during the second tutorial, so tutorial 2, we proved that the number of different neighborhoods in A is upper bounded by, now I think it was 4 to the power grad 1 of the graph plus twice grad 1 times size of A plus 1 for the empty neighborhood. I hope that this is correct. As far as I remember, this was the bound. Yeah? So essentially, what is exactly this constant doesn't really matter that much. What matters is that this is linear in the size of A. Right? So the number of different neighborhoods of vertices in A, yes, is always bounded linear in the size of the set. Yeah? So you see that here we were looking at the density of one shallow minors, and here we are thinking about neighborhoods which are like distance 1 neighborhoods. Right? Where we just look at the balls of radius 1. Yeah? So it's natural to think about generalizing it to larger distance. Yeah? So we can actually state this theorem that we will now prove. Let C be a class of bounded expansion. Let me fix R. Then there is a constant C such that for every graph from my class and every subset of vertices, let's say non-empty, the number of different distance R neighborhoods, so let me write it in a little bit hacking way as follows. Yeah, so I range over all the vertices of my graph, I take the set and I take the family of all subsets. Yes? So if two vertices u and u prime yield the same distance R neighborhood, then this set is only counted once in this family. Yes? Then this is bounded by linearly in the size of A. Yeah? So this is a proper generalization of this statement. Yes? By just saying that that instead of distance 1 neighborhoods, I look at distance R neighborhoods. Yes? The proof of this was based on just the density of shallow minors, and it was not that hard with very rudimentary tools that we had in tutorial 2. But for the proof of this theorem there, we will use generalized coloring numbers because this will become easier. Yes? I don't know actually of a proof of this statement there that uses only density of shallow minors. Okay, so yeah, let me start proving it here. Actually, we will not prove this statement alone, we will prove a stronger statement. And for a stronger statement, I need the following definition. So suppose again I've got a graph, I have a subset of vertices, and I've got some radius r, which is fixed. Then a distance r profile of a vertex u on A is the following function. Maybe before I write you the function, I will draw a picture. Here's my graph, here is my set A. Here I've got some vertex, and I would like to understand its interaction between this vertex and A. So the simplest possible interaction is just the distance r neighborhood. Yes? But now instead of just noticing how, like what is the distance r neighborhood, what are the like who is at distance at most r, I would like to measure precisely the distances. Yes? So for instance, for this vertex, I will see that it is at distance 10. From this vertex, I will see that it is at distance 5. And maybe from this vertex, I will see that it is at distance 3. Yes? And from the vertices outside of the distance r neighborhood, I do not care about the distances above r, so I will just put infinity. Yes? So this is like a distance function to A up to a threshold I, up to a threshold r. So let me now say it. So the profile at distance r of u on A is a function that to a vertex A from A assigns the distance between u and A if that is smaller than or equal to r, or infinity otherwise. Yes, so this is a distance function to A, just everything above r is replaced with infinity. Yes? Good. So what we will prove, so this object for A, for u, bears more information than distance r neighborhood, right? Because distance r neighborhood is just the set of elements of A for which this value is finite. Yeah? Good. So what we will actually prove is the following stronger statement. C bounded expansion, R is fixed. I've got my graph G, so then there exists a number C such that for every graph from my class and for every subset of vertices, the number of different distance r profiles on A is upper bounded by C times the size of A. This should be non-empty. Yes? So not only I will bound linearly the number of different distance r neighborhoods, I will even linearly bound the number of different profiles. So also the interaction with this neighborhood. Yeah? Good. So now with this in size, we can start proving it. Good. So as we want to use general coloring numbers, let's use them. So let sigma be an ordering with optimum weak coloring number at distance 2r, I believe. Yes? So what does it mean? This means that the weak coloring number 2r of sigma is bounded by the weak coloring number at distance 2r of my class. Yes? Which is a constant, call it d. This depends only on the class C and the radius r. Yes? Yeah, we just take the optimum, an ordering with optimal W column. So let me do the following. So let B be the union over all guys from A of their weak reachability sets. W reach, let me just check whether this is R or 2R. R, actually. Yeah? So I take every vertex from A, and I include all its whole weak reachability set at distance R. So how it looks on the picture is that here I've got my set A. It is somehow here scattered in this. And then for every vertex, I include all its weak reachability set, which just enlarges my set A to a larger set B. Yes? How much larger can B be with respect to A? These weak reachability sets, they are small. Yes? They are of size at most D. Yes? So what we have is that the size of B is at most D times the size of A. Yes? Oh, by the way, I will prove that the number of different profiles, so the goal is that the number of profiles is at most 1 plus, this is for empty profile, everything mapped to infinity, times D times 2 to the D minus 1 times R plus 2 to the power D times the size of A. This is our goal. So I will just put it here so that in consecutive steps we will see where all these summands come from, where all these factors come from. Yeah, this factor D will come from this, but this later. Okay, so we've got the set B, which is like a closure of A in a sense, slightly enlarge A in order to have more information on A in a sense. So now if I have a vertex U in my graph, I will define something that I will call a local separator of U and call it X of U. So this is local separator of U. And this is nothing else than the intersection of B with the weak reachability set at distance R of U. Of course, in the ordering sigma. Yes, I will not write it to save a little bit space. So how does it look on the picture? I've got here, maybe here is my whole graph G. Yes. Here is my set A. Here is my enlarged set B. Yes. And if I have some vertex U, yes, what I do, I take its weak reachability set, say it looks like that, and I take its intersection with B. Yes? So this thing is the X of U. Yeah? Okay, so clearly we have that each such local separator X of U is bounded in size, right? Because it is contained in this weak reachability set. Yes? So this is bounded by D. Yes, because all the weak reachability sets have sizes bounded by D. Good. So now we've got the following claim, and this is again something that I think was mentioned during a tutorial at some point. This is a very easy observation, but in a sense very powerful observation, and this is what stands behind all of these weak coloring numbers, is that x of u intersects all paths of length at most r from u to a. So how does it look on the picture? If I have any path of length at most r from u to the set A that I'm interested in, then I claim that this path needs to go through this local separator. Yes? And the proof is for the 10th time the same argument. Yes? So if P is such a path, then the smallest, say going from U to some vertex A, then the smallest vertex of P, of course smallest in my ordering sigma, belongs simultaneously to the weakly reachable set, weak reachability set at distance r of A, and in the weak reachability set of U. Yeah? Because this, if I take the vertex the smallest in the path, then the prefix witnesses weak reachability from U, and the suffix weak reachability from A. Yes? This thing is explicitly added to B. This thing is this thing. So this belongs to B intersection this weak reachability set, which is exactly this local separator. Yeah? Okay, so this is the proof of this claim. And from this claim, we can derive the following corollary. Oh no! Okay. We can derive the following corollary, which I again will write as a claim. Suppose I've got here is my B, here inside this A, and here I've got two vertices, U and U prime. And let me assume that they have the same local separator. So suppose x of u and x of u prime is exactly the same set. And moreover, the profile of my vertices u and u prime are the same. So, and profile at distance r from u on the separator is the same as the profile. Let's just call it x. Is the same as the profile of the other vertex. Yeah? So if this is a set X, what I mean by this is that this is the same local separator of u and u prime, and the distances from u to this vertex of the local separator up to threshold r are exactly the same for u and for u prime. Yeah? Then I claim that the profile of u on A is the same as the profile of u prime on A. So how to read it? This local separator sort of catches all the paths from u and u prime to A, right? So the distances that I see on X already determine all the distances on A. Yes? All the information flow between these two guys and A needs to go through this bottleneck. So what I see on the bottleneck determines me what I see on the parameters of A. Yeah? That's the intuition. Okay, so the proof, and the proof is again simple. Yeah? So what I need to prove suffices. to prove that for every A, from A, if the distance between U and A is at most R, then the distance between U and A is, say, larger or equal than the distance between U prime and A. It suffices to prove this statement, right? Because if I prove this, then this means that the distances from U prime can be only as large as the distances from U. But then I can take this statement and apply it the reverse way, for U prime instead of U and U instead of U prime, and see that the inequalities in the other direction also hold. Yes? So as far as I'm interested only in distances at most R, yes, I've got inequality in this direction, and also by the reverse statement, I've got an inequality in the other direction. Yeah? Then the distances to vertices of A will be the same. Okay, so why is it so? So let P path, shortest path from U to A. Yes? So I take this picture, I take U, yes? Here is some vertex A, it is a distance at most R from my vertex U. So there is some path, and this path, P, intersects X. Right? This is just this plane. This is a short path between U and A. Yes? So it needs to intersect X according to the claim that we just proved. Yes? So let X belong to the intersection of X with my path. Yeah, so this is some vertex X. So what I now know, this prefix of my path from U to X is a path of length at most R. Yes, because it is a prefix of a path of length at most R. Yes? So the distance between U and X is at most the length of this prefix. Yes? But these two guys had the same profile on X. Yes? So I know that the distance from U to X is the same as the distance from U prime to X. Yes? I can draw here a path from U prime to X of the same size as of the same length as this path. Yeah? So now I see I can go from U prime via this thing to X and then just continue to A. And I will not get longer by this way than the original path from U. Yeah? So this implies that the distance between U prime and A, this is upper bounded by the triangle inequality by the distance from U prime to X plus the distance from X to A. Yes? This is now equal to the distance between U and X plus the distance between X and A. And this was the shortest path from U to A, so this is just the length of P, which is distance from U to A. Yes? And I proved my inequality. Good. So what we know? We know that if I have two vertices with exactly the same local separator and exactly the same profile on this local separator, then they yield the same profile on A. Yes? So I claim now that it suffices to prove that the number of different non-empty local separators is at most d times 2 to the d minus 1 times the size of A. Now why so? Well, on a single local separator, because it is small, it is of size d, yes? Yeah, so on a local separator, of size, well, at most d, there can be at most, well, r plus 2 to the power d different profiles. Yeah, because every profile is just a function that to every vertex of this local separator assigns a number 0, 1, 2 up to r plus 1 numbers, or infinity. So there are r plus 2 possible values. Yes? And we know that if two vertices have the same local separator and the same profile, then they have exactly the same profile on A. So if we bound the number of local separators by this number, yes, then the number of different profiles on A will be bounded by this times the number of different profiles on these local separators. Yes? And this stupid plus 1 corresponds to the fact that I wrote here non-empty, because there are also vertices that have empty local separator, and these are exactly the vertices that are at distance more than r from A altogether. Yes? Good. So we now need to prove this claim. Okay, so let me take 6. I think I will just prove it directly. I will actually prove, we will prove that the number of local separators is bounded by 2 to the d minus 1 times the size of d. Yes? And recall that B was this closed set A, and the size of B was upper bound by d times the size of A. So this will be bounded by this. Yeah? So now I focus on proving this inequality. Okay, so let me fix one local separator. Let's say that X is a non-empty local separator, which means that X is just X of u for some vertex u. So how does it look? Here I've got my sigma. Yes. Here I have somewhere my vertex u. And here I've got my local separator. Well, it looks like more or less like that. Yeah? X of u. Again, draw a little bit more skewed so that I have more space. Here is my vertex u. And here is my x of u. And now recall how x of u was defined. X of u is just the intersection of B, yes, with the weak reachability set at distance r of u. Yeah. So in particular, all these guys here are weakly, are distance r weakly reachable from u. Yeah, this is why I drew them to the left of u in particular. Okay, so now we do something a little bit uncommon when working with general correct number. Namely, instead of taking the smallest guy from a set, we'll look at the largest guy from the set. Yes. So let B be the largest element of x of u. Yes, here is my vertex B. So now comes the crucial claim that I will write on the board. I claim that x of u is actually contained in weak reachability set at the distance 2r of B. Namely, all the vertices of x of u are weakly 2r reachable from this guy B. Yes? And the proof is, well, it's again the same story of just concatenating two paths. Here is my vertex u. Yes? Here is my local separator x of u. Here is my vertex B. So now all these vertices are weakly r reachable from u. So I can draw a path looking like that. Yes? Only to the right of B. And for every other vertex here, let's call him A, yes, I can also draw a path like that, a weak reachability path. This path PA is to the right of A, and this path PB is to the right of B. Yes? So then, the concatenation PA and PB, yes, is to the right of A because we chose B to be the rightmost guy. Yes? And this concatenation has length at most 2r, which gives me that A is in the weak reachability set 2r of B. Yes? Good. So now with this claim ready, I can prove that the number of different local separators is small. It's bounded by 2 to the d minus 1 times the size of B. And how do I do it? I just characterize every candidate for a local separator. So a local separator X can be characterized by the maximum of X in sigma. This is this guy B. Yes? And let's call it B. And a subset of its weak reachability set. I can exclude this B because, well, it is taken already. Yes? So in order to describe what is X, it suffices for me to just pick the largest guy, yes? Look at its weak reachability set, and say who from its weak reachability set at distance 2r also goes to the local separator. Yes? Because I have this claim. So how many options do we have? For picking the maximum guy, yes, we've got the cardinality of B options. Who will be the largest guy from my separator? And if I fixed already the largest guy, then this weak reachability set has size at most d minus 1 after exclusion of B. So the number of subsets is at most 2 to the d minus 1 choices for the subset. Yes? And we are done. Because we proved this claim there, which gives us the number of possible local separators together with the profile. By the claim, a local separator together with a profile gives me a unique profile. Uniquely gives me a profile on B. Good. Are there any questions?
Once again, what was the definition of D?
It
was just
This is just the weak coloring number at distance 2r
Okay.
of sigma. Yes. Almost all the time I was working only with weak reachability at distance r, which of course bounded by the weak reachability at distance 2r, up to this point. Yes?
Okay.
Where I used weak reachability for distance 2r. And this is why I chose in the beginning a slightly better ordering. Okay, so this was the proof of the theorem about neighborhood complexity in class of bounded expansion. This is always linear. And now, if you see all these parallels between bounded expansion classes and nowhere dense classes, you can ask what about nowhere denseness. Yes? And whether for nowhere dense classes you can prove a similar theorem, only the bound would not be linear but almost linear with additional epsilon in the exponent, as usual in the when going from bounded expansion to the nowhere dense setting. And this is indeed true. So now I can write it down as a theorem. So theorem C is nowhere dense. R is bounded. R is fixed. Then, and epsilon is fixed. Then there exists some constant C, such that for every graph from my class and for every subset of vertices, the number of different distance r profiles on A is bounded by C times the size of A to 1 plus epsilon. Yes? So instead of saying a linear bound, an almost linear bound. Yes? And in a sense, this is tight. We will see it during the exercises, I think, today, that if a class is somewhere dense and closed under subgraphs, undertaking subgraphs, then this number can be as large as 2 to the A. Yes? So there is a gap between for classes closed undertaking subgraphs. If it is somewhere dense, then this can be exponential. If it is nowhere dense, it is always almost linear. So there is a gap here. Yeah? So when you look at the statement, you think, okay, let's try to make the same proof. And do you see what fails if we try to make the same proof?
So the weak reachability number is not bounded.
Yeah, so we could W call, yes, at distance r, or 2r, of G, how it is bounded?
N to the epsilon.
By something like n to the epsilon. Yes? It's not bounded by a constant, it's bounded by the number of vertices to some epsilon. Yes? Of course, we are now looking here at the size of A to epsilon. Yes? But let's ignore it for a moment. Let's say that A is of size, say, linear in the size of the graph. So A to epsilon is the same as n to epsilon. Yes? This is actually not a big problem. The bigger problem is that if D, the weak coloring number, is bounded by n to epsilon, yes, then in this bound that we ended up here, we've got D's in the exponent. Yes? So just following the same proof gives us bound of the form something like 2 to the n to the epsilon, which is very bad because this is larger than n. Yes? So this is a problem, and actually it took us, I think, around 2 or 3 years to circumvent it. So essentially there is a way that we will probably see at the end of, just before Christmas, of using things called VC dimension to bound explosions like that. So in a sense, you perform the same proof, but you look at a certain set system, whatever it is, you bound this VC dimension, and instead of an exponential bound, you will get n to epsilon to some constant bound. Yes? So you use VC dimension in order to limit exponential blowups to polynomial blowups. But this is more technical work, but essentially the main idea of the proof is the same. You need just to patch various things in the proof using more interesting arguments. Okay, I think that's enough today for the lecture, and we see each other in half an hour for the tutorial.